Okay, good afternoon. This is Dr. Brown, and this is a list of the topics we're going to cover today in the video. First, we're going to look at the implicit differentiation problem, which was assigned over the weekend on Thursday. Then we're going to do a review of inverse functions. This is a topic that you've had in college algebra, and we're going to review this concept of inverse functions for just a little bit, and then we're going to look at how do you take the derivative of inverse functions. Then we're going to do a review of logarithms, and then we're going to talk about how to take the derivative of logarithmic functions. Then you'll recall that one of the easiest derivatives to remember is d dx of e to the x. You all know that it's the only function whose derivative happens to be itself. Well, we're going to then look at the derivative of the function y equal a to the x, where a is not equal to e. And after we do that, we're going to conclude by looking at logarithmic differentiation, which it turns out makes taking the derivatives of some functions that are quite complicated a whole lot easier. Now, going back to the problem we looked at on Thursday, we were asked to find the equations for the tangent and normal lines to the cissoid of Diocles. The equation is given as follows: y squared times parentheses 2 minus x equal x cubed. And we're going to find the slope of the tangent line by using implicit differentiation. So if you'll follow along here, we'll rewrite the equation. We will get 2y squared minus y squared x equal x cubed. And now we're going to follow the procedure of taking d dx of both sides. So d dx of 2y squared minus d dx of y squared x equals d dx of x cubed. Now, following the procedure for implicit differentiation, to take d dx of 2y squared, we first have to take the derivative with respect to y, which is 4y, and then we multiply by dy dx. That's the chain rule. Then you'll notice taking d dx of y squared x, that's a product, so we're going to use the product rule, and so we take minus the first, which is y squared times d dx of x. And of course, that's going to be 1 when we come back to do it. Minus the second times d dx of y squared equals d dx of x cubed, which is 3x squared. Now, we'll write down what we know already: 4y dy dx minus y squared. Dx dx is just 1. And then minus x. D dx of y squared, of course, is going to be 2y dy dx. And then we just copy down the right hand side, which is 3x squared. And now the procedure is to identify all of the terms with dy dx in them and factor that out. In this case, all of the dy dx's are on one side of the equation, so we'll just simply write down dy dx, factor that out, and we're left with 4y minus 2xy. And all the other terms, well, the only other term that's left is minus y squared, so it goes on the right-hand side, and so we get 3x squared plus y squared. And now we can divide by 4y minus 2xy to solve for dy dx. And we get dy dx is equal to 3x squared plus y squared divided by 4y minus 2xy. And notice, calculating this at the point 1 and 1, x equal 1 and y equal 1, we just simply get, plugging in x equal 1 and y equal 1, we get 3 plus 1 divided by 4 minus 2 equals 2, which we will call M1, which is the slope of the normal line, of the tangent line. Is equal to 2. Now, remember, we know that M1 is equal to 2. So the tangent line will be just simply y equal mx plus b. M is 2, and we need to find out what b is by plugging in the point 1 and 1. And when we do that, we get 1 is equal to 2 plus b. So b is equal to minus 1. So the tangent line, which is this line, is y equal 2x minus 1. Now, since the tangent line slope is 2, the slope of the normal line, or the one that's perpendicular at that point, is going to be the negative reciprocal, which is 1/2, minus 1/2. So now the equation of the normal line will be y equal minus 1/2 x plus b. And here we need to plug in 1 and 1. And so we get 1 equal minus 1/2 times 1, which is still minus 1/2, plus b. So b, as you can see, is equal to 3/2. So the slope of the normal line, or the equation of the normal line, will be y equal minus x over 2 plus 3/2. And of course, that's this line right here. Now we're going to look at the derivative of inverse functions and logarithms and logarithmic differentiation. First, we're going to review what is an inverse function. in very simple language, an inverse function is a function that will basically undo the original function y equal f of x. As you know, if you input x into f of x and get out y, then if you input this y into the inverse function, you get the x back. And this is the way it works for all functions of x. And basically, looking at a function in general that has an inverse here, y equal f of x, notice that if you input x1 into the function, you go up vertically until you hit the curve, then go and read off the value of y1 that corresponds to x1. Same goes if you input x2 at another point. You go until it hits the curve and then read off the value of y2. Now, what an inverse function does is let you input, say, y2 and ask the question, what value of x resulted in y2. And what you do is you simply go backwards and then go down, and you can read off the value of x2. Similarly, you would do the same thing for y1 and figure out what value of x1 produced it. So an interesting thing is that you can get the graph of an inverse function by just calling the y x and the x y, and then turning y vertical, and you now have graphed the inverse function. Now, here are some examples of inverse functions. As you already know, e to the x and ln of x are inverses of each other. So if you put x into the function e to the x, you get y out. If you put that output into its inverse function, you'll get x back. In other words, the overall function ln of e to the x equals x. In fact, you can make the general statement that ln of e to the anything equals anything. Another example of inverse functions are on your calculator. Tangent of x and inverse tangent of x are inverses of each other. You put x into tan x and get out y. Put that output back into inverse tangent of x, and you get your x back. In other words, inverse tangent of x equals x. In fact, inverse tan of anything equals anything.